Oh, I mustn't forget to turn this on. That's right. Can you hear me? Good. I recognise a few faces here. This young fella here from the Hamfests that I've been to. Ken Jewell, this bloke here. That's right. I've got a terrible memory for names, I'm sorry. I'm going to talk about paddy board, which is one of my favourite topics. In fact, I was talking about paddy board at one of the Melbourne Model Engineers meeting. They're mainly steam engines and aero engines and that sort of thing. But they're interested in electronics, a lot of them too. And I was waxing lyrical about this. And my friend who was in the group, he said, while you were giving your talk, I heard a bloke next to me say, "This fella's an evangelist." I am a bit of an evangelist because it kind of, it doesn't upset me, but you hear a lot of blokes on the air or you meet them in person and they're building something. They're going to build a power supply or a receiver or transmitter or something, and but they haven't made a start yet because they're looking to make a printed circuit board, or they're thinking about doing a printed circuit board. And I think that the thing that a lot of us miss is that we're hobbyists. We're not in the business of manufacturing things in their thousands. We make generally one for ourselves. You see a circuit in QST or AR or one of the magazines and you think, oh, I want one of those. You want to build it. It's a circuit board pattern there, and you think, oh yeah, I've got to, lay out a board or do something on the computer or buy a board in or somehow get a circuit board and then drill all the little holes and fiddle around with it and put all the components in and make sure that they're all the spacing so that they all get in the holes properly. And you build it up and it works, and it's fantastic. They're beautiful for kits, you know. You buy a kit and it's got all the individual components and you just put them in the hole. Very satisfying when it all goes together and you wire it up. Looks very nice and it usually works. But a lot of the time, when you're just sort of fiddling around at home or you want to try a little circuit or build up something even bigger, you want to just lash it up together and make it work, and often, like a lot of experimental things, it just stays that way. I forgot in our rush today, things have been a bit higgly-piggly at home today because the plumber came to put a new gas stove in and things like that, and I had to help him. I've forgotten to bring a model, but I think there's a good photo in the article, the paddy board article here, that is a pretty good illustration. The idea is that instead of laying out an ordinary conventional printed circuit board, the idea is to start with a circuit board. No, start with the circuit itself. You take an ordinary circuit. I'll take something simple, you know, we're all familiar with say you want to just build a simple amplifier. And you look at this circuit and you think, well, how many tie points has it got? You add them up. 1, 2, 3, 4, 5, 6. There's 6 points that you really need to wire to your supply line, and these points here. These could all be done with little pads. And what I do is I look at the circuit and I estimate the amount of area that I'll need, and then I have a bit of a think about it, and this doesn't take long at all, probably through practice. And I can have it cobbled up on a little circuit board in no time flat. Probably a quarter of the time that it would take somebody to lay out a circuit board and drill all the little holes and all the rest of it. It may not look pretty, but you've got to keep in mind who's going to see it. It doesn't have to pass inspection. There's no QA bloke's going to have a look at it. It's just for you, and it's going to go inside a box and it's going to work. And the beautiful thing about it, there's a couple of beautiful things, is that sometime in the future, if you want to fiddle around with it and change it, you can get in there, the thing's still facing you, it's in the box, it's been mounted in the box or whatever it is that you've made, it's all looking at you. You can get straight in with a soldering iron, undo any components, move things about, and modify it as required. If there's any fault finding, you're straight in there. There's none of this, hold it up to the light. Now, where does that connection go? I think it went, yeah, it's over there. You know, with a circuit board, you know what it's like, holding it up to a light, especially if you haven't got a circuit. There's none of that, because it's all laid out in front of you. Now, you might say that's all right for a transistor. What about things like a 14-pin IC? I'll give you a little demo in a little while. There's a little substrate that I've made. I call them substrates for a 14-pin IC. I just attach little wires to a nice machine IC socket and then make up a little substrate. And I used to use super glue to glue them down. The idea is that everything's copper side up. So say that's the circuit board that I'm going to put that IC on. That's copper side up. The IC socket is mounted on a little substrate which is also copper side up, and that I used to super glue them, but the problem with super glue is that, you know, you get about one chance to get it right and then it's stuck. You can snap them off the board, but lately I've been using hot melt glue. I'll try and give you a demonstration of hot melt in a moment. And I just wire my components to the substrate or whatever. I'll start that one going around. That's a 14-pin IC socket. Sometimes I get a bit lazy and I just go to Dick Smith or Radio Shack, what do I call them here? Tandy, and buy one of these little experimenter boards. This is I think this is a 24-pin or a 16-pin. Anyway, it's one of the bigger ICs that I've just soldered on there as a demo for you. Also copper side up, so the copper side of the board is facing up, and I've soldered it in very carefully so that the pins don't protrude through the little holes, so there's no shorting to foil. But have a look at that, you can see what I've done, and then you can puddle around with that with a soldering iron, develop something with a lot of ICs in it to your heart's content. And further, Vero board's very good stuff. This is a little 8-pin IC socket that I've soldered to a Vero board substrate. Just cut it out of a slab of Vero board, you know the stuff, you can buy it from J-Car or a few other places. I just cut it to size, solder my little machine IC to it. I've learned rather than to stick it in the holes, I've actually just planted on the copper part and very carefully solder it, and that gives me 8 little lands to which I can solder all my components. A carpenter bloke, a fellow that's a carpenter, brought a project of mine that he'd made and he couldn't get it going. And when I saw the way that he'd done it, I thought, brilliant, good idea, can I pinch that? Because what he'd done, instead of going to this Vero board business or trying to cut parallel lines, he'd worked out the angles, and they turn out to be 65 degrees, and I'll give you a demonstration of that in a little while. And you can take a little substrate and cut 1, 2, 3, 4 cuts on it, and then you can either solder your 8-pin directly to it or put a little socket there, which I have done. Have a look at that one. It's interesting because it concentrates the space right in the middle, and then it sort of expands it out for you to put your components on. So you've got plenty of room to work. This is one where I've used a wire wrap socket, and you can buy these quite readily. This gives you plenty of elbow room. This is built for HF and audio and logic circuits and that sort of thing. I wouldn't use it above about 2 metres. 432, I wouldn't consider doing it this way, but VHF and below, this is quite fine, and it gives you lots of room to work. You can even pass components. You know, your classic feedback resistor from output to input of a 741 or something, you can actually poke it between the pins rather than go all the way around. And it's a good way of doing it. And somebody might be thinking, yeah, all right, what about an SOE component? Well, there's a little 8-pin SOIC, small outline integrated circuit soldered to a 65-degree substrate. I had a little bit of trouble with that because I got a solder bridge, but it's just a matter of I've been doing that a fair bit actually with NE602s, for instance, the popular one. You can get them readily in an SOIC package now, not so readily in an 8-pin. So that's what I've been doing with NE602s. And here's a rectifier, power supply rectifier, just put on a four pad substrate. To work with this material, if you've got access to a metalworking guillotine, that's fine. You can guillotine you can get bits of scrap circuit board and that sort of thing. But even just an ordinary pair of tin snips mounted in the vise like that to give you a bit of purchase, and you can cut your little pads up no trouble at all. It's hard on the blades, but you can just sharpen them again. I cut these into little strips and pads as I require them. Like that. From model shops, and I think some craft shops, you can buy a little mitre box. It comes with a little, it's called a back saw, because it cuts on the back stroke like a Japanese saw. This comes as a kit, model shops and craft shops. It comes with 45-degree slots, but I've added 65-degree ones for the little substrates that I was telling you about before. When I'm preparing a substrate, I've got one here, it doesn't matter whether you use single-sided or double-sided, it really doesn't matter. I've been using single-sided lately. If I'm preparing, say, you won't be able to see this very well, but say an ordinary 8-pin substrate like that one, I'll start with a cut just down the middle. This is ordinary hardware shops have these, just a junior hacksaw. You've probably already got one, most blokes. I make a cut across so that all the copper's removed, and then a cut along so that all the copper's removed, like so. And then I just estimate halfway between those two and halfway. Oh. Do you want to get a close-up of that if you're interested? Can you see it? Yep. And halfway again. And oh, I forgot to bring my glasses too. No, there it's. But that's what you end up with. You have a real good look at it, make sure that you've actually got all the copper away. For the substrates which have the 65-degree angles, I use the ordinary little junior hacksaw to just to divide down the middle. Don't worry about trying to remember all this because it's in the notes here. I've brought some copies of the article. That's a division halfway down, and then I use the back saw because it's got a very fine curve. The junior hacksaws are a little bit coarse in that it leaves quite a wide curve, and then a 90-degree cut, and then I move to these 65-degree slots, by the way, I did with a engineer's protractor, not a posh one, just one of the little, the ones with the little moving arm, just to get the 65 degrees. It happens to be 65 degrees. There's that one. So you can imagine something with 4 or 5 or 6 ICs in it. It's not going to take you long to prepare a little substrate. I'm fairly pleased with that one, so I'll send it round. I think I might have oh no. Now I collect all these, keep all my scraps, cut them all up. That strip, for instance, I would use that as a battery run. Battery run is supply rail run. positive 12 or positive 6, and I would run that the length of the circuit board. You can see that in this photo. Have a look at it later if you're interested. If you study the photo in this article, you'll see a strip that carries positive 12 volts, I think, along the board. You'll see the ICs mounted on their little substrates and various other single pads. They don't have to be multiple pads. There's a multiple pad which might take this circuit here, would give me the 1, 2, 3, 4, 5. Well, there's 4 pads for my transistor and its various devices, and then I might just run a little supply rail past it for the various stages. They don't have to be square. In this article, which I will present to the librarian, that's the American, they call it Manhattan, presumably because it resembles a New York City grid, 90 degrees. Paddy board, by the way, is not an invention of mine. Does anybody remember Roy Hardcop? Yes. Dear old fellow, lateral thinker. He's strange. Very strange. He coined the term paddy board, and he was using it years ago. I should tell you something about the history of it. This was started by a fellow called a Canadian bloke, can't remember his name, VE5FP, I think. He had an article in Ham Radio magazine in about 1970 something, and our own Harold Hepburn did a similar amplifier using paddy board in the early 70s, and that's where it was introduced to this country, and it's kind of taken off since then. You don't have to use square ones. You could, if you're really keen, make something like this. The American article shows that you can buy some punch arrangement from one of their big hardware places, Walmart or somewhere. But I've made this thing, which is various size holes. Can I bang on this table? Yes. But I haven't brought a hammer. Is there a hammer in the workshop?
A hammer, please. It's coming.
What a radio club that's got a hammer.
I've got a workshop, tool shop.
I made this thing. It came out of a book called Electrical Things Boys Like to Make by Lindsay Publication. Google Lindsay one day, Lindsay Publications, and see what you see there. He's republished a lot of the a lot of the old classics, and this was in it, something of this kind. These are ordinary, scroll pin punches that mechanics use to punch out scroll pins and that sort of thing. You can buy them in sets from any of the motor spares places. But just put your circuit board in there, and you can bang them out as required. I'll bang it right through, actually. And you get these nice little pads, and you can just glue those to the... I have to ask again for something from the workshop.
Oh, no worries.
It's an extension cord.
Extension cord?
Yeah, I'd like to plug in the glue gun. Will it do? I'll plug in the soldering iron too. I should have done that right from the start, because I'll give you a demo of how easy it is to use the... This is a little glue gun from a craft shop. You can get the bigger glue guns from Bunnings and that sort of thing. Just talk among yourselves while I untangle this thing.
I'll do that for you while you're doing something else if you like.
That's all right, I'm nearly there.
Yeah. Oh, wait, till the right time, you want a...
No, I think this will do. Thanks very much. Okay.
Leave it here anyway.
We'll let that warm up. I'm a latecomer to hot melt glue. I reckon it's terrific stuff. There's only one disadvantage with it. It melts. So whatever you use it with has got to be pretty cool. I think I might plug the soldering iron in too, because that's all part of it. When I start building one of my little paddy board circuits, before I glue anything, I generally have an idea on a piece of paper just how many pads I want and where they shall go, and then I cut them out to size accordingly, and then I will place them on my main circuit board exactly in the place where I require them, just placing them there, not gluing them yet, like pieces on a chessboard, and just put them there. The other beaut thing about paddy board is that there's a lot of flum. You don't have to worry too much about resistors and capacitors because you've got so much room. You just solder say I need to solder a resistor between one of the pads and ground. Well, you just bend the leads of the resistor, cut them to length, solder it onto the pad, solder the other end onto the ground foil, and you've got the component in. I do wish I brought the project to show you the photo, but there's been plenty of examples in AR in the last few years that you can have a look at. When that's warmed up, I'll do a gluing demonstration and a soldering demonstration. If on those really close spaced ICs and things, if I get a bridge, I just mop it up with a bit of solder wick, which is quite easy to do. You do really need a magnifying glass if you're going to get really, into very small ICs and you want to make sure that it's all right. When they are warmed up, I'll be able to give you a demo of putting one of these onto the board, gluing it on. It's pretty good idea to give your board a scour with a Scotch Brite or something. Make sure that there's no fingerprints or grease or tarnish there that's going to prevent you from soldering, because you want to be able to solder onto that board without any mucking around. You want to be able to just solder down to it each time. Now, with any luck, the little glue gun should be working. What I've found in practice is that the glue gun doesn't always stick first time. So what I've found is a good plan is to put a little bead of hot melt glue on the bottom of the pad, put it in position exactly where you want it, and you see that hasn't glued because I've been mucking around for too long getting it into position, but that's no great trauma because you're going to be soldering to it anyway. So what I've found is a good follow-up is to just tin the pad, and you can usually get enough heat from your soldering iron when you apply it to the pad to do a really good job. And the other thing is it slides around all over the place, but that's beaut because you can put it exactly where you want it. Did you see that? The blokes at the front probably saw it. When that's set, that won't easily come off. We'll leave it to dry. And you realise from that, of course, that, oh dear, I put it in the wrong spot. I want to change that. Out with the soldering iron, put it on the pad, move it to where you want. And again, I'll give you a demo. With super glue, I don't know if you've ever tried to solder through super glue, you just about pass out. It's worse than peeling onions. The fume that comes up out of it is unbelievable. Your eyes water. I believe it's cyanide gas. So, yeah. But with, even if you've got a bit of hot melt glue on your circuit board and it's in the way, it's no great trauma because you can just, I'll give you a demo, I'll solder right through the stuff and I'll put a blob on the board. There we are. You can solder through it. It's almost like a flux. So it doesn't get in your way, even if you've peeled it or scraped it off the board. And the smell from it's not too bad. It's actually pretty good. I don't mind the smell of it. Heaven knows if it's dangerous or not. Now, have I covered everything? I think I have. Any questions so far on paddy boards? Right. I hope I've made a few converts.
Drew, what about capacitors from the pads down
It's 4 puff per square centimetre. Generally it doesn't get in the way, but if you're working at VHF like and I've done 432 meg projects with this stuff, you just make your pads as small as you really can and just work with that in mind. There's a converter that I published a few years ago, 432 meg converter. I made the strip lines for the input and tune circuit and the voltage multiplier out of strips and soldered and glued them down to the board, which became the input filter and the crystal oscillator multiplier filter. I think that's enough of paddy boards. No questions about paddy boards. All right. Another thing I'd like to talk about is coils. Coils are a hot topic. As you tune around and talk to blokes, tune around on the bands or talk to blokes, they're all building a tuner, C-H-U-N-E-R. A more correct term is probably a coupler, but I think we all know what we're talking about, commonly known as an antenna tuning unit. There's been various patterns. One that you'll often see in American publications, and I'm going to get stuck into the Americans, because for years and years and years they've promulgated this transmatch thing, which is and your transceiver goes on there and it wants to look into 50 ohms, and your antenna goes on here. And these are a couple of variable capacitors. This is it's a very good circuit. It's capable of matching into from 50 ohms into quite a wide range of impedances. There's 2 disadvantages with it, is that it's a high pass element, which is no great trauma because most modern sets have got a low pass filter in them anyway. The other thing is that it's unbalanced, and a lot of the antennas that you want to feed, things like loops and dipoles, and that includes the G5RV, which is a dipole. These are intrinsically balanced. By balanced, I mean that the instantaneous current in the line at any point is the same amplitude but then flowing in opposite directions, and the instantaneous voltage at any point in the line is the same with respect to Earth. And that is a balanced antenna, which a dipole is naturally balanced, and so is a loop naturally balanced. You take your balanced dipole or loop, you want to put it through this coupler or couple energy through this coupler into your balanced antenna. We all know that you can't just simply, well you could, but it would be improper operation. You can't just connect your dipole like that, or you shouldn't, because you'll have unequal currents and unequal voltages applied to the line and it won't be operating in the correct manner. So the Americans and a lot of other people say, put a balun in. Well, a balun's fine. Say you've got an antenna that presents you with a beautiful 200 ohms here. You could put a balun in there and match into that 200 ohms. No worries, but as we know, when is it 200 ohms resistive? It's usually some other value and it's got capacitance in it or inductance in it. It's all over the place. How do you match? The Americans still put, I'm blaming them because they've propagated this thing for years and years since the late 60s. They jam in a 4-to-1 balun here. You adjust this up. You will get a 1-to-1 SWR here, but they never invite you to measure the current. If you measure the current in each leg of the line out here, you'll probably find that in most circumstances they're unequal, which means that you're not getting the full advantage of a balanced antenna. It's complete. It's to do with, I don't know, the laziness of doing things in the modern way. For years and years and years they had in their handbook what you would call a truly balanced coupler, and I built a few of them and they really do work. The trouble is that they've got a lot of variables. You start with a link, your 50 ohm from your transceiver goes in there, then you've got to organise a coil like this, which has got some kind of a split stator capacitor across it. You can ground that or that, but not both. Most people ground that. because the frame of the capacitor is common anyway. So you float that. It's a mistake to connect those two together because they may be unequal. You can take your balanced transmission line, you don't know what impedance it's going to be presented, and you can connect it into your coil, equidistant from the centre. You can short out shorted turns. Now I'll just mention about shorted turns while we're here. A lot of blokes think, oh, shorted turns, just like shorted turns in a transformer, it'll mean a loss. It doesn't mean a loss. Transformers, ordinary transformers working at 50 hertz, have got a unity coupling. They've got a core in them, and anything that happens in the primary or secondary is immediately felt in the other winding. They are coupled tightly, but an air-cored open winding solenoid like one of these, the coupling's not one-to-one. So shorting turns is not an issue. Your short turns, for the very good reason that if you do that, if you leave that end open, so you're well into the winding, you're only using a few turns and you've got 20 turns out the end here, just floating, you can develop terrific voltages here, and some blokes have got into terrible trouble with arcing and all that sort of thing off the end of the coil. By shorting the coil, you get rid of that problem, and it doesn't alter the Q whatsoever. If I took that Q and measured the Q of it, and then shorted out half the turns and measured the inductance, it would be a lot smaller inductance, but the Q would still be high. The only caveat on that is that you do your short circuiting with a very low impedance path. So that was covered by a fellow called Ian White, who's got his own web page in England, shorting out unwanted turns. Anyway, this coupler is a little bit clunky. You've got this is usually a dual gang broadcast gang. That's there to just tune out the residual reactance that always arrives here. This is a 1 or 2 or 3 turn link. This is sometimes made switchable. These are tapped, usually tapped. This is a variable capacitor. You don't really have to use plug-in coils. You can make a setup like this work from 3.5 to 29 megs, no trouble at all. The ORRL handbook and the RSGB handbook had this arrangement for years and years and years. But then they got lazy because you couldn't get split stator capacitors. Does anybody know the Johnson Matchbox? Arguably the best balanced antenna coupler that was ever made. What they've got is, instead of an ordinary single unit dual gang, like a broadcast gang that we would use, they very cleverly got a dual differential in there. They've got it arranged so that when that capacitance is going up, that one's going down, and the same with that one. That one will be going down when that one's going up. And then they can retune it with another one. And your unknown impedance or your antenna feed line goes on there, so you can imagine you're getting the equivalent of being able to move, with this mechanism, move it up and down the coil to wherever you want smoothly and losslessly, and this one will resonate it. The Johnson Matchbox, there was a Johnson Matchbox and a Johnson Matchbox Junior. If you see one at a Hamfest, it'll probably be about $500 or something, because it was arguably the best. The thing that's stopping fellows from building these at home is the problem of this capacitor, this magnificent thing here, which is a dual differential. It just stops you from building it that way. So they kind of got lazy and went to the T. And I've gone through various iterations of that. 2 balanced couplers, which are very good, I'm happy with them, but they all use the link, which can be variable if you want to, but it can be fixed. But I finally settled on a balanced pi coupler, which is this one here. I'll draw the circuit out. It's simply a two coils arranged like that. Normally you would have just one capacitor here, but we have trouble getting high voltage transmitting capacitors. So what I've done is used dual gang broadcast capacitors. So they're about 450 puff. So they're connected effectively in series. This is the frame. So this is gang 1, gang 2. That's the common connection through the frame. And the same one here. When I first tried this, I made the mistake of grounding that and grounding that. Shouldn't do that because you can never get things perfectly balanced. So you just let them float. Let them float. You still get your capacitance range. So you've got 450 puff there, 450 puff there. So your total capacitance is 225 is the maximum you can get. That side and that side. Antenna goes on there through the feed line. Here, I have got a bellon. An ordinary so-called voltage bellon. I don't like the term voltage and current bellon, but never mind. That's an ordinary 3-winding bellon. That's a true bellon. This sort of thing where that side's grounded and that side's supposed to be 50 ohms balance is all right. It's I'd call it a quasi-bellon, or Wes Hayward calls it a sort of bellon. It's not a perfect bellon because you can get imbalance here. You need that third winding to force equality here, so that if you measure the voltage here with respect to ground, this point with respect to ground, anywhere in the spectrum, it'll always be half what's applied here. So if I apply 100 volts there, you get 50 volts there and 50 volts there from maybe a couple of hundred kilohertz through to 30 megs. I use a loop stick there, a little bit of loop stick. It doesn't have to be anything posh, even ordinary broadcast band loop stick will do. The great beauty of this is that the bellon is in the low impedance side of the circuit. This impedance out here, I don't know what it is. It could be a high impedance, it could be a low impedance. If it's a high impedance, the series inductance will supply the required series reactance. So that acts as your current choke anyway, which current choke might be asked to do. You've got series inductance here. This floats, so you've got this impedance in series. This can be used to match from 50 ohms to, I don't know, anything from maybe 20 ohms to 1,000 ohms, so it's got a terrific range. The inductors are made variable by having taps, just ordinary, I've just made these coils so that I can tap into every winding, and this will work from 3.5 to 29 megs. If this bottoms out, in other words, I run out of capacitance, I'm looking for more capacitance, the way things work, if this is a high impedance circuit, I won't need a lot of capacitance. I'll be using probably what's provided by the capacitor, even if the voltage here is maybe 1,000 volts. The broadcast gang capacitors, you might think, oh, there may be low voltage working, but they're in series, so you've doubled the voltage rating of the capacitor. And it's unlikely that I will need a high capacitance here. On this side, I may well need a low, if this is a high impedance antenna, I may well need, on 3.5 megs for instance, I might be looking for more than 450 puff. I've simply got these silver microcapacitors which I can plug in as required. I can plug in 1,000 puff, a 270 puff, or a 500 puff, or I can stack them one on top of the other to give me a total of, I don't know what it is, 1,500 puff, like that. Silver mica, because they're very low loss, they don't get hot. Don't use those little blue things, they're a waste of time. They get hot, they can even burst or explode. They're not, they're too lossy. So that's the balanced pi coupler. That appeared in AR a few years ago, and it's in volume 4, I think, of my book. So, and that's a really good coupler. I like it, and it's not fiddly to tune. You find that these are fairly broad in their tuning. So I've fitted verniers on here, but you don't really need them. it's just convenient to have a number. And a little look-up chart. A band change takes about 20 seconds. Clip lead, dials in the right position, because I've set it all up beforehand, and you're in business. Final little tweak because it's been raining that night and things are a little bit different, but it works really well, up to 120 watts. I don't know what it's like beyond 120 watts. We get onto coils. Before I demonstrate how these coils were made, I'd like to talk about coils a little bit. I did a study of coils. I got very interested in them there for a little while, because you read and you hear about on the grapevine that, a coil should be really be silver plated if it's to be any good. The beauty of silver plating is that it stops oxidisation, and the oxide of silver is an insulator, so that the conducting part of it just below the oxide is still as good as ever. That's a silver plated coil. Now I made a bunch of coils, a group of coils, all with exactly the same inductance, all with the same gauge copper wire, but treated them all differently. I wasn't working in the dark because one of the fellows in our labs, Alan Fowler, does anybody remember Alan Fowler, radio engineer? He designed the tuning units and the diplexer at 3LO 3IR back in the 50s sometime, and that's his coupler in Radio 1 and Radio 2, the publication that we all had. Anyway, he did a publication on silver plating coils and went into it, and he plated coils with all sorts of materials to see how the Q was affected, and he came to the conclusion that if you're going to silver plate a coil, then it has to be done properly. Most silver platers do decorative silver plating, and it's got a little bit of cadmium, I think, in it as a brightener. What's the brightener? Does anybody know? Is it copper? Anyway, the decorative silver platers is what you'll get. If you take a coil down to the silver platers, they'll give you decorative silver plating used for utensils and things like that. I'll get onto that in a minute. Remembering his article about silver plating, I made a group of coils. This coil is made with ordinary tinned copper wire, so that's tin on the outer surface of the coil. This is a plain coil, the wire I got from George White, that's just plain copper wire. The same coil as that one, but I made it go all green and horrible by putting uric acid on it on a daily basis, which I supplied. And it was all green and horrible because I was interested to know if the corrosion lowered the Q at all. It looked pretty horrible, I can tell you. I cleaned it up before I measured it on the bridge. There's still a little bit of the green left, but don't be afraid, I've washed it. And I measured the Q of all these. Now, if I can remember, this plain coil has a Q of 350, that's plain copper. The tin-plated coil, which is very nice to work with because you can solder to it and it doesn't really corrode very much, that was 340, so it's only a small amount less than the plain copper. Now, one writer in AR said, enamel on a wire, it lowers the Q. Well, this has got a Q of 340, enamelled copper wire, so it's the same as plain copper wire. Also rather nice, doesn't tarnish, looks good for the life of the equipment that you put it in. This one, the horrible old green mouldy looking thing, 330. So, coils in old equipment that are starting to look a bit daggy and corroded, it's still quite good. You've got to remember that the current, we all know about skin effect, don't we? I don't have to go into skin effect, do I? The current flows in the copper part on the outside. The bit of oxide on the outside is immaterial because it's an insulator. So it's not an issue. Same with transmission lines. This piece of transmission line, if that was outside and it all gone green and horrible, in fact I did it once. I made a piece of wire, a piece of transmission, not as long as that, about half that length, measured its loss, and over about a 6-month period, dipped it in salty water and made it go all green and horrible. It was a 0.5 dB loss from one end to the other, with a proper bellin at each end, and then I measured it after 6 months when it was all green and horrible. It was exactly the same loss, exactly the same loss. So even in the transmission line, it's the same. The silver-plated coil is the same Q as the... And you might think, well, what's the skin depth of this? I've done the calculations. You have to go back to old books like Terman's Radio Engineering to find the formulas, but the thickness of that copper is about right. In other words, the current flowing in that coil is, the thickness of the plating, I'm sorry, the current flowing in that coil is in the copper, in the silver. One thing you've got to avoid is using, for any kind of coils, HF, wherever you're working, don't use stranded electrical wire, because it's 7 strands. 1, 2, 3, 4, 5, 6, 7. There's 1 strand in the middle and 6 on the outside. It's a mathematical geometry thing. That's why it's 7. They all touch. You're expecting skin effect here, and you're asking radio frequency current to flow over this sort of a surface, and it's disrupted. Not only that, but what a lot of fellas forget is that although it's an inductance that you've got here, there's also minute capacitances between each turn. And if you've got insulation upon the wire that's of indifferent dielectric material, and the material that they use for electrical wire has got flame inhibitors and all sorts of things in it, and it's got colouring in it, might even have carbon in it if it's black, it's not a very good dielectric material, and you've got those as capacitance in your high frequency coil between each turn. So best not to use ordinary insulated electrical wire if you can at all avoid it. The coil I wound like this, I haven't brought it with me, it's not here, but there's a coil just like that, wound with ordinary electrical wire. Its Q is 240, so it's 100 less than any of the others, proved by measurement. One of the most popular couplers, and it's a good one too, was the Z-Match, promulgated by Lloyd Butler. It's an English design. It was in the RSGB handbook way back in the 50s, reproduced and modified. KW made it as a Easy Match, if you know that one, the Easy Match coupler. That's of the same circuit. It uses a coil, a single coil that's wound on a piece of perspex like that. The idea with winding a coil on either that way, I have described doing it this way, but you need a little jig and bits of wood, and it's all right. And you can come up with a coil like this. The idea of making open or skeletal coils like that is you've got the minimum of dielectric material. You've got turns that are separated from each other. You've got no former. All these things, all this dielectric material in the field, in the electric field of the coil, all becomes part of the capacitive arm of the coil. So you've got to reduce the amount of dielectric material in the coil. That's all right. Mounting it, generally you've got to put a bit of perspex in there anyway to mount it on a couple of standoffs or something. By spacing it like this, you get the ability to put your tap in there anywhere you want to put it. So that's rather good too. I don't mind moving alligator clips. For some reason, some blokes like to be able to put a switch in there, but it usually makes things a lot more complicated and the switch becomes unreliable. With an alligator clip, when you've clipped it on, you know that it's probably made pretty good contact. Anyway.
Drew, is that an enamel coil you've got on your particular one?
It's enamel, but I've scraped the insulation off.
Oh, you've scraped it off?
Yeah, right there, just on the top. Yeah, sit down patiently. And that's right, you've got to, just on the top, have a look at it later, you'll see that there's enamel to there and then it stops because I've got along there and scraped the enamel off. It is a bit laborious, but it's put the radio on and just sit there and do it. I've forgotten where I was now. Oh, the coil. The manufacture of these sort of coils only gets a very brief mention in the RSGB handbook of I think it was the fourth edition, where they say you wind the coil and then you screw it through a piece of perspex, but they don't give you any clues about the dimensions. And I tried to make these coils and I couldn't make it work. I'd get the bit of perspex and I'd drill holes and I'd wind my coil, and then I'd try to screw it in, and I'd get about 4 turns into it, and it'd jam up and it'd go to one side and I couldn't get it through, and I thought, what am I doing wrong? And that's why I went for this sort of thing. But I revisited this and I thought, what am I doing wrong? Because the Poms can do it, why can't we do it? And it's to do with marking out accuracy. So instead of drilling the holes first and then making the coil, I had a brainwave. Make the coil first and then make the holes. What you find is, when you wind your coil, a vodka bottle's beaut because it's about the right dimensions. It's 56 millimetres across, and it's got this beaut handle on one end. So you can anchor your wire. I get a pair of bullnose pliers, pull the wire, get all the little wrinkles out of it, and then I just tape one end, wind it on. Now, this is 19 turns. What you find is, almost universally, I've tested this, when you wind it onto a mandrel, like this bottle, when you've wound it on, what you get is an unwinding of 1, 2 turns, virtually. So if I want 19 turns, I've got to wind on 22 turns, because it'll unwind 2 turns, plus lengths for your tails, so your terminating tails, like that. So you need a little bit of extra. So you calculate the length of wire you want, which is pi times the number of turns times the diameter. Yeah, plus a little bit more for errors and the What you then also find is that the diameter increases by 13 to 14%. So when it unwinds, not only do you go back 2 turns, but the diameter increases by 14%. So with a little bit of arithmetic, you can make an estimate as to how big your perspex blank has to be. Perspex, by the way, you don't have to buy it. You go down to a plastic sign maker. He'll have a scrap bin. Tell him that you're there. He'll say, help yourself, and you can go home with an armful of perspex, free for the asking. That's what I found in Ringwood anyway, and Bayswater. So you don't have to buy it. And it's really good stuff, the stuff that's manufactured now. It doesn't shatter, it's got a fair bit of give in it. You've got to mark this out very accurately. I'll show you in the notes here. This is a lead-in. This part here is the inside diameter of the coil. So when my coil's wound, then I make the blank. This makes a beaut lead-in because as you screw the coil in, you've got this part where the coil is already supported, and then as you begin to screw it into your helix, I like to call it a helix before it's a coil. Before it's wound on, it's a helix. You wind your coil patiently through the, I think there's a better one than that, through the holes, and you find that if you've been accurate in your marking out, the coil will just be nicely there. And what you don't want is friction. Accurately mark out your holes, and I countersink them just a little bit so that the coil will smoothly screw its way through the holes. Have a play with these later. You should find that without too much difficulty, it's generally easier if you put it in a vise or something like that, and then you can just sort of, there we are, screw it through there. See how easily that's going through? It's not perfect. I didn't do a very good job with this one, but it's good enough. There is a little bit of friction. You're talking probably a fraction of a millimetre in accuracy, but this one's not bad, and it's going through quite nicely. And you can get the whole coil in there. There's the last turn going through. There. When I'm happy with it, I'll just put some araldite or hot melt glue down each side and let it sit. If you're using araldite, it's a good idea to hang it up because the araldite will remain liquid for a while. It just drops off the end, cements it in there nicely. I think there's one or two. There's one that's, is that hot melt? This is hot. This one's hot melt because you can feel it's a little bit flexible. These ones are araldite. They're both araldite and hot melt are quite good at radio frequencies. You can put some in the microwave, see what happens. It doesn't get roaring hot. It's quite good. I think I've covered everything. Any questions? No more? There's...
What do they call it? Litz wire in coils.
Everybody talks about Litz wire. It's really only good to maybe 1 or 2 megs. I notice switch mode power supply people use it, but I think they use Litz wire not for the reasons that we understand, but so they can wind thick wire in small spaces. I think Litz wire is pretty much a furphy because you can't buy it now anyway, unless you're prepared to make it yourself. In little broadcast coils and that is probably all right, but for transmitting coils, I don't think it would give us any great advantage, especially at HF.
One place that I've found Litz wire is in the deflection yoke of large CRT monitors.
Yeah, they use it in a few places like that, I noticed. I don't know where you'd buy it though. I mean, it's only good, it's no good doing it at HF. It's only good at maybe 1 meg and below. With our new 135 kilohertz band, 36 kilohertz band, it could get renewed interest, but obtaining the stuff is the problem for most people. You've got to use, even buying ordinary enamel copper wire. The last time I bought a coil of this, I had to buy the whole coil from O.H. O'Brien. It was over $100. Fortunately, I was able to spool it off and sell it on to other blokes. But if you only want to make 1 coil, you're probably better to go to an auto electrician or an armature winder or somewhere like that. Tell him what it's for. He'll say, yeah, beauty, I'll give you some. And that's the only way you'll do it, I think. Anything else?
I wonder, you mentioned the electrical wire is not for obvious reasons isn't good. Have you tried it for twin lead or for antenna wires?
It's all right for antenna wire.
Yeah.
Yeah. I wouldn't use anything else because it's flexible.
Yeah. And for twin leads? Or leadings?
No, I wouldn't use twin lead for lead-ins.
So I mean making it out of electrical 7-strand.
Oh yeah, I use, you can't buy it anymore, but you used to be able to buy 7-strand earth wire that had no insulation on it. Butte stuff. No, I think that's all right.
I've got a 300 metre roll of it.
Yeah, can't buy it anymore. Oh, I think that's the lot. No more? Nobody went to sleep as far as I know. This bloke here was dozing off.
Well, thanks very much, Drew.
Can I turn this off?
Hope everybody's enjoyed themselves and learned a lot about it. I certainly did. And we'll